Hello. So in this video, we're going to be computing another limit. This one is, again, this sort of ratio of polynomials. And so as sort of is typical when we have one expression that we're trying to take a limit of, the first thing we're going to do is try plugging in the value and see what happens. Again, with the sort of idea that it's not likely to work directly, but how it goes wrong should tell us, what we need to do to get the actual limit. Okay, so I'm just gonna go ahead and sort of plug in this, right, x going to 3. So I'm gonna plug in 3 to this overall bit. So I'm gonna have 3 squared minus 3 times 3 minus 4 divided by 3 squared minus 2 times 3 minus 3. So again, I'm just plugging in 3, I'm going to compute now. So 3 squared is 9. 3 times 3, 9 minus 4. 3 squared, again, is 9 minus 2 times 3, which is 6, minus 3. So 9 minus 9 is 0, minus 4 is negative 4. 9 minus 6 is 3, minus 3, 0. And unsurprisingly, it didn't go the way I would like, so I'm a little sad, but it's not terrible. It's not all bad news, because the way that this, again, didn't work tells me what to do next. So I tried plugging in, I got this thing that looks like a non-zero number over 0, and what that tells me is that this thing is sort of behaving badly in some sense. In particular, what it's really telling me is that I'm trying to take some non-zero number and divide it by something that's getting really, really close to 0, right? So if you divide by some really, really, really small number, like 1/10, 1/100th, 1/millionth, right? When you divide by something very small, it's the same as multiplying by something really big, right? Dividing by a small number makes things bigger. And so what's happening here is that this thing is trying to go somewhere near this non-zero number divided by 0, so it's blowing up, it's getting huge, is what's happening. The problem is that because it's 0 on the bottom, I don't know if it's really close to 0 on the positive side. I don't know if it's really close to 0 on the negative side, right? And what I'm dividing by, if it's negative, then this is getting really big, and negative over negative would be positive, right? So it's getting really big and positive. On the other hand, if it's really close to 0 on the positive side, then it's negative over positive, and it's getting really big negative, meaning that like which side of 0 it's on is pretty important to know whether it's getting really big positively or really big negatively. So this is the thought process that's occurring. This is what we have to go hunt down now. And the way we do that is that we're going to use a sign chart. In order to use a sign chart sort of the easiest, the first step is to factor as much as possible what we have. So this tells me, in particular, that I'm going to want a sign chart. And hopefully this is familiar from like pre-calc or grade school. If it's not, don't worry, I'm gonna cover it here. But as the first step of the sign chart, the first thing I'm going to do toward that is factor. Factor. Okay, so I'm going to take my overall function up here. So I have this x squared minus 3x minus 4 divided by x squared minus 2x minus 3. And I want to factor this thing. So again, factoring polynomials, if you're sort of rusty at that, there are resources available to go through all of that. So here, factoring this, they're both coefficient method. I'm going to end up with x minus 4 and x plus 1. And in the bottom, I'm going to end up with x minus 3 and x plus 1. Okay. Now, it's worth a mention here that I have a common factor. And in another video, when we had a situation where we had this sort of ratio of polynomials, I could cancel out the common factor, and now my limit worked, right? But that was the case where I had something that was 0 over 0, right? So if it's 0 over 0, I would expect that I would have a common factor, and that factor is what's causing those zeros to exist. Since I don't have 0 over 0, I may still have common factors, and it's not a bad thing to simplify, as we'll see, but that isn't sort of causing the underlying problem, meaning that if I cancel these out and try again, it's still not going to work. And the reason why is because we're taking this limit as x goes to 3, that's causing the 0 here, not the common factor, right? So it would make simplifying a little bit easier in some sense, but not, it wouldn't sort of meaningfully change the problem and make it so I can compute the limit right away. Okay, so I could simplify this. I don't have to simplify this. I'm going to leave it unsimplified for the sake of showing the whole sign chart process, but if you simplify it, I'll explain why that's fine too. So once I've done this, excuse me, then I'm going to do the sign chart bit. So to do the sign chart bit, I'm going to make an X number line. And I'm going to put on this, I'm going to mark on this number line only the zeros of the factors, okay? So I have, for example, -1, which is in both places if I didn't simplify. So I'm going to have -1 here. I have a 3. That's maybe somewhere over here. And I have a 4. Notice that I didn't put in like 0 as a default spot, right? A lot of people, when they make a number line, they're like, oh, I have to have 0 sort of in the middle or something. But I didn't put that down because that's not a 0 here. As a mention, I will say that if you did put 0 down, it wouldn't make it wrong, but it does generate more work for you to do. So you'll eventually still get to the right answer, but you'll be kicking yourself because you do more work to get there, okay? All right, so now that I have this thing written, in order to do the sign chart part of this, what I want to do is between each value and beyond, so like I need something that is to the left of -1, something that is between -1 and 3, something that's between 3 and 4, and something bigger than 4. So each sort of region is what I'm looking at, right? What I want to do is sort of test a value in there for what the sign is, positive or negative, in that region. So for example, if I'm looking between -1 and 3, I could take 0, right? 0 is between -1 and 3. And I want to check to see what happens if I plug in 0 here. Do I get a positive thing or a negative thing? Okay. And I'm going to do this in a little bit of a weird way, but it's way faster, trust me. So bear with me a second. I'm going to look at each factor plugging in 0. So I'm going to do 0 minus 4. That's going to be a negative. That's all I care about. I don't care that I know it's -4. I just know that it's negative. Then I'm going to do 0 plus 1. That's a positive. Again, I also know that it equals 1, but I don't care. I just care it's positive. Same down here. 0 minus 3 is negative, and 0 plus 1 is positive. So this tells me that if I plug in 0, I'm going to get a negative times a positive in the top. So that's going to be a negative. If I plug in 0 in the bottom, I'm going to get, again, negative times a positive, which is a negative. And that means that I'm going to have a negative divided by a negative, which is overall positive. So that tells me if I plugged in 0, I would get a positive number. Okay? Now, you might be saying, like, okay, but how hard is it really to do, like, 0 minus 4 is -4 times 1 is still -4. That's, I could have written -4 here instead of just negative, right? Why do I have to make it all abstract and concept-y? But there is actually a good reason to do this. And for the next one, we can actually see. So if we want a number, we need a number between 3 and 4. Now I don't have a nice whole number to choose from. I could choose, say, 3.5, right? Now, if I did that, if I choose, say, 3.5, then I do 3.5 minus 4. 4 is bigger, so I'm going to get a negative. So let me maybe block this off. So if I did that up here, I would get a negative, because 3.5 minus 4, the 4 is bigger and it's subtracting. 3.5 plus 1, positive. 3.5 minus 3, now the 3.5 is bigger, so that's going to be positive. And 3.5 plus 1, right, positive plus positive, still positive. So that's going to get me a negative times a positive is a negative in the top. divided by positive in the bottom, which is overall negative. So I have a negative here. Now my claim is that I'm gonna, that this is a demonstration of why I don't want to use actual numbers, like in terms of computing it all the way out, right? So with 0, it would have been relatively easy. 0 minus 4 is negative 4. 0 plus 1 is 1. 1 times negative 4, negative 4. Right? 0 minus 3, negative 3. 0 plus 1, 1. Negative 3 plus times 1, negative 3. Negative over negative, blah, blah, blah. Okay. But if I'm doing 3.5, now suddenly I have 3.5 minus 4, right? So I'd have to get a common denominator, plug through all of that. I end up with a negative 1/2. 3.5 plus 1. Now I need a common denominator again. So that's going to be 3.5 is 7/2 plus 2 over 2. So that's 9/2. But then I'm multiplying by a negative half. So now I have like negative 9/4 or something. So as soon as you sort of get intervals that are not nice, right? They don't have nice integer values between. And by the way, like, sign charts are used in a lot of different areas, and I might end up with something like a number between 3.7 and 3.78, right? And then you're like, okay, I have to use like 3.75 or something. And now doing these computations becomes awful. Whereas if you're in the habit of just being like 3.5 minus 4, the 4 is bigger, so it's negative. Bam, right? You don't actually have to go through the crazy rabbit run of computing out and like dealing with the fractions and stuff. So it's good to sort of be in the habit of doing these with just looking at positives and negatives, because they sort of save you a lot of computation time down the line. And in the spirit of this, we can do this, we can take this sort of to an extreme when we're looking at the endpoints, right? I need a number less than negative 1, right, to the left of negative 1. I could choose negative 2 and do this and it would be fine. But since I could pick any number to the left of negative 1, I'm going to choose negative 1,000. Why? Because it's going to overpower these plus minus things to the point where they're irrelevant, right? If I have negative 1,000 plus 1, that's still negative, right? This plus 1 is nonsense. The minus 4 is nonsense compared to a negative 1,000 or negative 1,000,000 or negative a googolplex, whatever, right? And so it allows me to very quickly be like, negative 1,000,000 or negative 1,000 minus a small number, that's negative. Negative 1,000,000 or whatever plus 1, still negative. Like, I don't even have to think about this anymore. So if I'm way to the left, I'm going to get negative, 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 negative. They're all the factors are negative because this plus or minus some small number does nothing. So I'm going to get negative times negative is positive. Negative times negative is positive. Positive over positive. So this is going to stay positive. All right. And likewise, if I picked some number to the right of 4, I could choose 5, but I could choose 1,000,000,000, right? That's also in that same range because it's any number bigger than 4. And if I do 1,000,000,000 minus 4 or plus 1 or minus 3, it's not going to do anything. It's going to stay some large positive number. So I'm going to have positive, 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 positive. That's just going to stay positive. Okay. So this is my sign chart. This is how you do a sign chart sort of overall. It's sort of worth a mention here, like I did a little more than I needed to for this problem because I want to show how to do all of the sign chart bit. And I said at the beginning, or sort of beginning of doing the sign chart bit, I would mention why this x plus 1 bit, whether you simplified it or not, didn't make a big difference. So if I had simplified out the x plus 1, it wouldn't have been one of my factors, one of my zeros, right? Which means I wouldn't have put the negative 1 here, and I would have had just this range, right? I wouldn't have had it broken up into 2 pieces. But as you can see, they both ended up positive, so I didn't actually have to test both of these things, right? So if I had simplified it out, I would have just seen that this whole range is positive. But since I didn't, I broke it up into 2 pieces and found that both of them are positive. This is why if you have extra things on your number line, it doesn't lead you to a wrong answer, right? You'll still get the right answer, assuming you do the rest of it right. But it generates more work because you have to test more sort of intervals. Okay, so how does all of this help us when it comes to actually getting the answer to our limit, right? So let's remember what our limit was. So this is the limit as x approaches 2 of this whole big thing, x squared minus 3x minus 4 over x squared minus 2x minus 3. Now, because this thing was if we remember right, non-zero over 0, this is telling me that I'm going to have to look at this as the left and right pieces. So I'm immediately going to write this as limit as x goes to 2 from the right of x squared minus 3x minus 4 over x squared minus 2x minus 3, and the limit as x goes to 2 from the left of x squared minus 3x minus 4 over x squared minus 2x minus 3. Okay, so I've broken it up into, I'm gonna make this a little bigger, hopefully you can see that. I've broken it up into the right and left limits. And this is going to always be the case, so you always need to break it up when you have this non-zero over 0 thing. And the reason why is that we need to see what happens in those regions as I'm getting close to 3, right? As I'm getting close to 3 from the left versus close to 3 from the right, I need to know what is happening. When we talked about this over here, we said it's getting infinitely large, but I need to know sort of, is that positive, right? Is it getting positively large, or is it negatively large? So now that I have my sign chart, I can tell. A very common mistake to have happen here is that people use the sign chart for where the 0 goes, and that can get them in trouble because the sign chart is everything. It encompasses all of the function because we did all of the function here. I mention that because if you think, for example, like to the right of 3 is negative, so I'd have a negative over negative, and that's positive. No, that's not right. Here, what this sign chart is telling you is that the whole function is negative between 3 and 4. It doesn't care that you had some negative 4 over 0 bit over here. This is everything. So this is telling me that if I'm to the right, so if I'm looking at the limit from the right of 3, the whole function is negative. And the fact that it's this non-zero over 0 tells me that it's going to infinity, and it's going to infinity and staying negative. This tells me that the thing is going to negative infinity. As a side note, sometimes, depending on your person that is grading, your teacher, TA, whatever, some people will rather you do an arrow here. Some people may let you use an equal sign instead, so they may do something like this for the bit. This is a very sort of pedantic thing in mathematics, and there are people that care a lot about that, and there are people that don't care a lot about that. So you should ask whomever you have in terms of whether they want the arrow or the equal sign, or if they don't care. So here, from the right, so bigger than 3, between 3 and 4, it was negative, so that's how we got negative infinity. From the left, I'm a little bit to the left of 3, the whole function is positive, again, blowing up to infinity, so this is going to be positive infinity. Now, I have the limit from the left and right, the limit from the left, limit from the right. So the overall limit, this thing can only exist if these things are the same thing, but they aren't, One's negative, one's positive. This tells me that the limit as x goes to 2 of this overall thing, x squared minus 3x minus 4 over x squared minus 2x minus 3 does not exist, D, N, E. Okay, and in particular, we know that because these things are not equal, These are not the same value. Okay, so I was a little bit longer because I wanted to really jump in and do the sign chart bit fully so that you can see that for all of the places we'll use it, which this is going to come up a lot, so practicing sign chart is useful. But overall, for the original problem, we have this whole limit of this whole sort of block of stuff. So as usual, we plug in to see what happens, knowing that it probably won't work directly, but how it goes wrong tells us what to do. When we did that, we got this non-zero over 0, which told us we needed a sign chart. To the sign chart, we factored, we found all the regions, and we found the sort of functions values in all of these regions in terms of like positive, negative. Since this was non-zero over 0, that told me that it was going to and infinity was getting infinitely large, either positively or negatively, and the sign chart told us which way, right? So when I looked at it from the right, the function is negative, so it's going to negative infinity. When I looked at it from the left, the function is positive, so it's going to positive infinity. And so the overall limit, since these are not the same, does not exist. Okay. So in this video, we're going to be computing another limit. This one is another piecewise limit. So as is sort of usually the case, we're confronted with the piecewise. The first thing we want to do is find where this sort of limit point, the x value of interest, right, what we're limiting to, where that is in the domain. And again, as is usually the case, here it's one of those transition points between the two values. So this means that, again, as is usually the case with piecewise limits, we're going to have to break this up into a left and right version of these limits. So the first one I'm going to do, I guess, again, it doesn't matter which order. I could do a limit from the left or a limit from the right. So I'm going to do the limit as x goes to 0 from the right, let's say, as my first. Sorry. There we go. So I'm going to be doing the, again, breaking this up into the left and right. So if I'm looking at this for f of x, this means that I want to do an x value to the right or slightly larger than x. So I go back up to my domains for my piecewise and find where x is slightly bigger than 0. So here x is bigger than or even equal to 0, but we don't care about the equal part. It's that it's bigger. So that's what my f is in that range. So this is the limit as x goes to 0 from the right of what it equals, this negative 2x minus 1. And here, right, if we're doing the, we're computing this limit, but once we have it to this point, we don't really have to care that f of x was originally some piecewise thing. Now this is all I need, right, to figure this out. And this thing is a line, that's a type of polynomial, and that means that this thing is continuous everywhere. Specifically, it's continuous at 0, so I can just plug it in. So this limit is equal to minus 2 times 0 minus 1, which, right, again, now that I've plugged in the value, the 0, I shouldn't write limit anymore. So negative 2 times 0 is 0, minus 1 is negative 1. So this is my limit from the right. Okay? So the next up, I'm going to do the limit as x approaches 0 from the left. And here, right, so again, I want values to the left are slightly smaller than 0, so I go back up at my domains, and I look, and I see indeed this thing, right, x is less than 0, so it's to the left of 0. So my f of x is this function over here, this 3x minus 4. All right, so that means that I'm going to have limit as x goes to 0 from the left of 3x minus 4. Okay? But again, now I don't have to worry about, what f of x was, the fact that it was this annoying piecewise thing. I have it just this bit now, and that bit, this line, polynomial, continuous at 0. So again, I can plug in 0. So I'm going to get 3 times 0 minus 4, which is 0 minus 4 is negative 4. Okay. And last but not least, I now look at these, compare these two, right? So I look at the limit as x goes to 0 from, let's say, the left of f of x. This was negative 4, which is obviously not the same as negative 1, right? Different numbers. But that negative 1 is what the limit as x went to 0 from the right of f of x. That was what that limit equaled, right? So this limit was negative 1. This limit was negative 4. Those are not the same. So since the left and right limits do not agree, meaning they are not the same thing, the limit, the overall limit as x goes to 0 of f of x does not exist. Okay. So again, we had this limit of this piecewise, so we checked the target of the limit, right, that what it was going to, which is 0, found that it was indeed one of these transition points from one function to the other. So we broke it into the from the right limit, from the left limit, computed them, found they were not the same, and since they're not the same, the overall limit does not exist.